Hello and welcome to the lecture in Convolution Neural Network Part 1. In this particular lecture, we are going to introduce the Convolution Neural Network, popularly known as CNN, and what is the typical architecture of the Convolution Neural Network. We will discuss convolution, pooling and local contrast normalization, and then we conclude this CNN for just discussing an image recognition task. Today we will start convolutional neural network, what is popularly known as CNN. This CNN is a deep neural network that uses these convolution layers for automatic feature learning from data. Now that we have to understand what do we mean by automatic feature learning using these convolution layers. There is some properties or characteristics of CNN. Here, first of all, these convolution layers actually apply multiple learnable filter kernels to detect or to model local patterns such as edges, texture, shapes or simple statistical structures. Initial layer basically model the simpler structure or the later layer with the complicated patterns. Okay. Now, in this convolutional layer, the neurons are generally connected to a small local region. For image, you can say the image patch, rather to the entire image. Okay, that also we try to understand why this kind of characteristics are being in CNN. Now, another important characteristic is weight sharing. What does this mean? Weight sharing is basically using the same filter or same filter kernel, or you can say set of weights across different spatial location. Now, some neuron is basically used for a particular patch, but the similar weights being used for different spatial location. What advantage will get? It reduces the parameters, number of parameters, and it improves generalization. That also we're going to see in this lecture. So basically in this slide what we are basically trying to understand, what do we mean by CNN? Very simplistically, the CNN is a deep learning network which uses this convolutional layer, and there is some characteristics that what convolution layers do, what a neuron is basically used for small local region and weight sharing done. Now, first of all, understand what are the very basic building blocks of the CNN. It's a very in general structure. So, in C, there is a convolution layers that have been used to extract the local spatial features. Then, another important aspect is pooling layers. Pooling layers are basically going to use for reducing the resolution and for retaining the dominant information or most important information. Okay. Then there is another thing is called imposing nonlinearity. This is being done by using activation function, and there is some normalization is being done by local contrast normalization, etc. That essentially stabilize the training and add expressiveness to the network. Then after this is done, basically this particular area where actually this feature extraction or automatic feature extraction are being carried out, after that these features are fed to the fully connected layers. So this integrated feature for decision making. So this is a kind of, you can say, not specifically is very, these are feature extractor, these are classifier, but some kind of, so decision making, so as a classification. And finally we use the softmax kind of layer that converts output to the class probabilities. So now these are the in general structure. Always all the things are being used. That maybe sometimes maybe it's possible normalization is not used or pooling is not. In general, convolution and this activation are being used. So these components are being stacked flexibly to build this shallow or a very deep network. So what thing we have to understand here, that this particular one, this equals level kind of thing, that essentially have convolution, nonlinear activation, normalization and pooling. And then this kind of several such layers having this kind of architecture. After that, it may be not, it is not 4, it may be 40, maybe more than that. And then when the feature is being extracted, fed to the fully connected layers and ultimately the softmax to get the predictions. As we have seen before, that there is certain difference between the conventional machine learning approach and the deep learning approach for a classification task. In the conventional machine learning approach, there is an image and there is some manual feature extraction. Sometimes it is called feature engineering. So we have some sort of features. There may be geometrical features, there may be statistical features, or there may be some patterns or kind of object like features. Now after extraction of these features are basically fed into some neural net or any other classifiers, and which essentially do the predictions or give the inference. That was the standard approach for the conventional machine learning. So as we understand, there is mainly two things. One is feature extraction, another is classification for these predictions. Now for our deep learning approach, this image is fed to a single network, and this single network at the same time doing this feature extraction and this classification to make the predictions. So in deep learning model, it is a automatic feature extractor as well as the classifier to do these predictions. Now with this background, what we have to understand, that what are the basic building blocks of this deep neural network. Since we are basically now discussing convolutional neural network, first we understand what is the very naive structure or very basic structure or generalized structure of this convolutional neural network or CNN. Now what we have seen, that an image is basically fed to some level of networks, or you can say some one layer. Now this layer of architecture or kind of these layers of this deep neural network is basically produce the low level features. Very hypothetically, this low level feature is fed to another this kind of layer, and this will give the mid level feature, and it is subsequently fed to this another. This layer will give the high level features. Now it may be possible that just for a very hypothetical presentation, we have made it a single layer. It may be multiple layer here for this low level features, multiple layers for mid level features, and multiple levels of high level features. So there is only 3 for very simplistic case. It may be 30, it may be more than that. Okay. So, but what we have to understand here, what is the architecture of this layer. Okay. So this particular layer is in general consist these blocks. First of all is convolution block, that will come next, what the convolution do. Then there is activation function that we have seen before, that may be a sigmoidal activation, some ReLU activation, leaky ReLU activation and so on. And then there may be some state of normalization. Some example, maybe a local contrast normalization, and then another important step is pooling. So these 4 steps are in general part of a single layer. Okay. Now it may not always the case that this normalization or pooling are a part of this layer. Maybe, may not be, but in general this is for the general structure or general component of these layers. Okay. Now one by one we see what these components are in our next course of these slides. Now what is important, this part, these low level features, mid level, high level features, hypothetically creates this automatic feature extraction. Okay, and this feature, what has been extracted by these layers, is fed to the fully connected layers. Now again, hypothetically we can use a 3 fully connected layer. It may varies. It essentially give you some sort of decision, or this kind of, not decision, you should say some values. Okay, and these values are fed to the softmax or equivalent kind of layers, which essentially give you some probability kind of values. Why I said kind of? Because in general softmax gives the probability value. Other things may be other value. Based on this we can get the class level or any other if any regressions and some values there. So as a whole, this is the full essence or full structure of a CNN. So what is important? There is this kind of layer which is composed of convolution or linear activation, normalization, pooling, and after such this kind of multiple level of these architectures, what we get, this feature is fed to the fully connected layers and then ultimately fed to the softmax kind of layer and we get the predictions. So these are the basic structure of this convolution neural network. Okay. Now with this background, we'll see that what this effect of this convolution, or in other way we try to understand what the convolution is essentially doing here. Why people use convolution? First of all, I again go back to our previous thing. What is the basic essence of convolution here? It is extract local spatial features. Now it extract local features. Okay, that we are going to understand, that how this convolution layers, okay, is extract these local spatial features. Okay, so this convolution is a kind of a signal processing strategy, or is a kind of way for this kind of image processing or data to image transformation task. That's for edge detections. Okay, you'll find out some edges of in a given kind of, if there is the object boundary can be understood. Then blurring or smoothing effect possible by this convolution kernel, or convolving the convolution kernel with the images. Sharpening can be done. This is a kind of filtering, is basically. And by virtue of these things, we can extract features. So feature extraction is basically this, that we are going to see that this kind of pattern is essentially present in this particular portion of the image or not. That is the job of convolution. Okay. Now we are going to understand how the convolution operation is being carried out in CNN. Now, as we have understood before, that convolution is being done, or it is used to find out the pattern or local spatial pattern in the image patch. To understand that a particular this pattern, just for example here, we are searching for a horizontal line. For this searching of a horizontal line, we used this convolution kernel as this. Now you can see there is a zero crossing in this horizontal direction. If you go for this vertical direction from 1, 0, 1, you can say there may be some sort of this kind of pattern will come. It looks like a kind of horizontal line. Now what we have to do with this kernel, we convolve the image patch, this patch wise convolution. So what initially we first do, we put this convolution kernel over the top left portion of this image. So we take first this 3 cross 3 image patch and we put it here, and we then what we will do, the element wise multiplication. For example, 5 into 1, 5 into 1, 5 into 1, then 5 into 0, 5 into 0, 5 into 0, and then 5 into minus 1, 5 into minus 1, 5 into minus 1, and then add all this like this. So we get 0, so we put it here 0. Okay, so this way we calculate. So when it is been done, then we shift one position right. Since we shift only one position right, this kind of sliding window or this kernel in right way in one position, we call the stride here is 1. If it is strides 2, from here we go there, so that will be this position and so on. Okay, again we do this element wise multiplication and add it all these multiplications, we get the value. Again it is a 0. So if we keep on doing this, we can get this position, we can get this here, this. So first this patch, this first, we'll get this first row of this resultant pattern, and we keep on doing this. Now in this way we'll come here, okay, in this like this. Now again we'll do 5 into 1, 5 into 1, 5 into 1, then 0 into 0, 0 into 0, 0 into 0, and 0 into minus 1, 0 into minus 1, 0 into minus 1, we get the 15. Now we put 15. Similarly, first to the 15, this also 15. And we keep on for all this. Now, very interesting to see here that what a kind of pattern we get. You see, it's a, if you say the black is 0 and white is 1, 0, 1, 0 pattern kind of. So it clearly indicates there is some sort of horizontal line pattern there. So by essence of this, by visualizing this, we can say, okay, there is some sort of horizontal line here, because you can see here it's a 5 and it's a zeros, and there is some sort of horizontal line is there. So in this way, this convolution operation try to find out some basic pattern, some very primitive pattern like this, some horizontal line, maybe some vertical line, some slanting line or whatever. So in this way, this kind of convolutions being done. Before we going next, one thing must understand. Now, this convolution kernel here, for understanding this idea of convolution, we use this fixed kernel. But when we put this convolution kernel to the convolution neural network, these kernels are not fixed like this. Rather, these kernels are learnable kernels. Okay, that we learn what will be this kernel, so that we can do for a particular layer, for a particular neuron, what will be the best kernel for a particular application or a particular mapping, input to output mapping. So every neuron for every layer has a contribution to this, and this learning is being done automatically, okay, from this input to output. Since we are now discussing the supervised domain understanding or kind of supervised learning, then based on this our input output mapping, we can learn these kernels. That is the one may be confused with this. So to understand that how convolution work, we use the fixed kernel. Okay, now we see here that what we are, this pattern, this horizontal line pattern we find here. So with what we have understood, that using this kind of kernel, okay, we can find this. Okay. Now this is the some example, some practical example of this. Then searching for a similar pattern. If we have some particle filtering, filtering means that we have to find out where these particle lines are there. So vertical edges is there. So some similar kind of filtering or some similar kind of kernel we used, and we found this image. These are the vertical lines exist here. Similar is for horizontal edges. So we have this kind of this was a very simple kernel. So that kind of kernels will be used. Find this kind of horizontal lines here, that we can understand that this given this picture, this particular image, we can find the horizontal edges or vertical edges by virtue of this convolution of a certain kernel, and that is very important. So that thing is very important to understand here, that these convolution operations are used to find out a particular pattern, maybe vertical line, maybe horizontal line, for a very initial layer. But when we go to the some higher layer, then they are basically some complicated patterns that trying to find out by this virtue of this convolution kernel. This convolution kernel is more complex to find this, and so on to this. So what is we observed here, that image statistics tend to be locally consistent with these small regions. Now this is very important observation. Now what we have understood or we have been said before, that some local area like this are given to a single neuron. Why? Not every full image is going to be a single neuron. Rather, a small patch is given to it. This is because if you consider an image, there is a very interesting observation that a local patch or local neighborhood is have a consisting or very homogeneous image statistics, or rather in that we can say a small neighborhood is statistically homogeneous for image, and this homogeneous portion we are trying to find out by virtue of a single neuron, so that this neuron is very effectively find out this some local characteristics or local patterns of it. Maybe this position can be another neuron, that position is another neuron, and so on. So that's why what we say, the nearby pixel exhibit strong correlation. That's why we said statistical homogeneity is there in a local portion or a local neighborhood, because the nearby pixels or the neighboring pixels exhibit strong correlation. So filters can be reused across the spatial location to weight sharing. If we go back in a very fast slide here, that we can say that each neuron is convolution layer connected to a small local region. That we said will this is the reason. Since an image, a local portion or a local patch or a small portion of the image, the statistical homogeneity or of the pixel is very high, or we can say image is very locally homogeneous, a pixel with strong interpixel correlation. Okay, that's why each neuron or a single neuron is attached rather the entire input. Okay, entire input means entire image. Another thing, that same weight parameters are being used across the different spatial location, reducing the parameters and improving generalization, since that same thing we are using here. That filters can be reused across the spatial location through weights here. So exactly this is the weights, the initial weights may be this. So what is the benefit? This result significant reduction in the model parameters, so that we can say reduce number of parameters and achieve good generalization across. So these are the very important observation of doing this convolution in such a way. Okay, so in CNN we do this, we according to this observation in normal image processing or standard image processing practice. So each hidden neuron connects to a small local region of the input like this. The same set of weights is applied across the different spatial locations, the weight sharing. Weight sharing leads to a significant reduction in parameters, and any neural network includes convolution layers referred. So this is the right definition. So as a kind of summarization of the very first layer of this, what we have seen that this in this convolution layer, maybe any kind of these patches, these image patches, because this is the very initial layer, because the input is image. So this the local patch is basically or local region or a small image patch is going to a single neuron rather the full image to a single. Okay, because of this, that nearby pixel exhibit strong correlations or interpixel correlation is very high in a local neighborhood. Okay, and another thing, maybe the weight parameters are being shared across these neurons, and because to reduce the number of parameters and for a better generalization. Okay. Now we are going to understand how the convolution operation is being carried out in the practical scenario. Let there is an image patch is 32 cross 32, and let again we say there is a RGB image. So there is a 3-channel image. One is for R, red channel, one is for G, green channel, and B, blue channel. So ultimately the total image dimension is 32 into 32 into 3. If you do this, we can get 3072. For fully connected layer, in general we can represent this image of this 3-dimensional image to this vector. This is 1 into 3072. That means it is a ones number and such 3072. That's why this 3072 is coming to 32 cross 32 into cross 3. Now this vector of such dimension is convolved with this convolution matrix. Now, what is the dimensionality of convolution matrix? It is 3072. If there is a one convolution matrix, this is 3072 into 1, but here we can get 10 such. So, ultimately this convolution matrix is dimension 3072 into 10. Okay, now if you convolve it, then we can get for a single row of this convolution matrix, we can get this one scalar value, because this is 3072 1 cross 3072 into 3072 cross 1. So it is a 1 by 1 scalar value, and such 10, so there will be 10. So this black dot is basically a scalar number. This is the case of in the fully connected layer. Now we'll come to the initial layer, that means the input. Input is 32 cross 32 into the same. Now this is given in this way. So that is 32 cross 32, and there is a 3 channel, red, green and blue. And our filter dimension, as we mentioned before, it is 5 cross 5 into 3, because these 3 should be equal to this. So now what generally happens, as we discussed earlier, that this filter kernel or convolution kernel is placed from a certain position and slide over the whole image patch. Okay, so we convolve or slide over all spatial locations, and if we do this, we can get this resultant image, or we can say activation map. So what we basically going to do, this particular convolution kernel, we convolve with each of the location, and then we get a single scalar value. This is one dimensional, and this is a single value, and such, since it is a 32 cross 32 image of size 3, and this is 5 cross 5 filter of depth 3, or here depth we consider channel or depth, same thing. So we can get such activation map. Okay, now you can ask that from where we came this 20k 28. Now here we can the same example. This is the 32 cross 32 cross 3, this image patch, and we use the 5 cross 5 kernel, convolution kernel, and we slide over all the spatial location. Now here, now let this 32 cross is capital N, this 3 is there, so n by n into 3. This is image patch size. Similarly, the convolution kernel size, now this f is equal to 5, so f cross 3. And we also discussed what we mean by stride. Stride is basically how we are sliding. Since we are sliding, or we assume that we are sliding only by one element or one position, that means the stride is 1. So how we get the output size? So this k value, this is a k is equal to n minus f. So this n minus f by stride. Now in our case stride is 1, so n minus f, that is 32 minus 5, 27 by 1, 27 plus 1. So this is the formula of deriving the output size. So it is 28. In this way we get the 28 here, and definitely this 3 1, so this is 1. So the activation map is basically 28 into 1. This is the dimensionality. So okay, in this way our convolution kernels are being used for the convolutions. Now the question is, how many such convolution kernels are there? For this example, you can see there is a 6 convolution kernel. So this is again the same image patch. Now k different convolution kernel. For this example, k is equal to 6. And if there is a k different convolution kernel, there will be 6 different activation maps. Okay, such that this we are giving the 6 different color for these 6 different activation maps. Why we are giving these 6 different kernels? Because each kernels is basically searching for a particular pattern. Let's say first kernel is for horizontal line, second kernel is the vertical line or edge, and this is for some sort of slanting and so on. So this is the way we can find a different kind of pattern. Since it is a input first layer, so the different kind of very primitive patterns. So, and the corresponding activation map or resultant map, whatever we can say, these are the 6 different. So in this way we can find that what are the different primitive patterns are present or not by virtue of these convolution kernels. It may be, in this example it is 6, it may be more than that. Now, since we have said that in our convolution neural network is a series of convolution, in between there is other layers, but this is a series of convolution. So how actually this is being used? You can see it is starting with this input patch 32 cross 32 into 3, and then we use the 5 cross 5. So as per our this equation, n minus a by stride plus 1, and here we always the stride is 1. So it is, as we know, this is 28 by 28. Now from this 6 is coming. Now 6 such kernels are being used here. So it becomes this width, that means this basically depth kind of thing is basically 6. Now again for this we use 3 cross 3 kernels. Okay, and you can see that now we have used this kernel size. This depth is 6 because it should be aligned with this number. So 6 into 3 into 3. It was before 3, that was the depth was 3, that was 3 into 5 cross 5. Now 6 into 3 cross 3. And how many such kernel we have used? 10. So now it has become 10. So this step become 10. And as per our this equation, if we use 3 cross 3, 28 become 26. It's very easy. 28 minus 20 minus 3, 25 plus 1, because stride is 1. Now again we can say, we can next step, next convolution, use a 12 filter of dimension 10 cross 3 cross 3, that is, since it is 10, this should be 10. So it's become 24 because of this 3 cross 3, and it's such 12 such filters being used. So this become 12 and so on. In this way we can understand, in this way our convolution works in a successive layers for a convolution neural network. Now the basic thing what we have learned here, this is giving an image patch, and this is the first layer of activation, and a single kernel, it may be a horizontal line or a vertical line we are searching. Now that will generate this activation map, that is kind of finding where is the this for a particular patch, is there any horizontal line exist or not in a different position here, and that will generate a map. We can get a very practical example. This will come in our next lecture, that is the AlexNet structure. It is a very renowned kind of deep learning network or convolution net, that these activation maps for first hidden layer is like this, And here you can say there is a 64 this filters. That means these convolution kernels, this is the single activation map, such 64 such activation maps are being used. Okay, and here we can use this 11 cross 11 convolution. Okay, that is the, and then we can get this 64 different activation map which is being stored in this way. So this is the first layer. If you visualize the what is the output of the first hidden layer, that or activation maps of the first hidden layer for this AlexNet, and what this 64 filter kernel are being used of the dimension 11 cross 11, 3 cross 11 cross 11. This. Now we can understand how actually are things being done, or we can understand that how this convolution operation is going to understand that if a particular pattern is exist or not. So what we have seen that the convolution determines that a particular pattern, this specific patterns like horizontal line, vertical line, etc., are present in the input or not. But there is some mechanisms also required, that is to emphasize certain patterns over others at a given spatial location. So what is required? Now there is a, let's say there is a 10 filter kernels of different pattern. Now it is not possible that in a very small position there is a more than one patterns. So what is required? We have to understand what is actual a prominent pattern and others are basically maybe noise, maybe not so prominent. So pooling is such an operation that achieve this emphasizing some pattern over the other pattern by selecting the most prominent feature response. So for example, the maximum activation. Okay, so this operation is very important for understand which pattern is most prominent among all other patterns for a particular image batch or a particular local region. So in essence, what pooling is basically doing, it reduces the spatial resolution of an input while preserving the most significant information, and that is the basically the job of the pooling. Now here you can see there is a some sort of 9 different tunes. So basically these are the, you can say, the kind of patterns. Okay. Now this pattern, that which pattern is most important or most prominent among all these patterns, and that is defined or that is determined by this pooling operation. There is a different types of pooling. First we start with maximum pooling. Now if this is an activation map or is basically the filter response of this convolution. Now what we are going to do for this particular, what is the highest value? This is 6. So max pooling selects the largest value in a region. So this is 6, so it will give 6. Okay, so this emphasizes the strong features. That means what is the prominent feature that we are going to select. Next, what will come? Next, it is next position, and what is the highest value? 5. So it will give the 5. The 5. And in this way we are doing the mass. So what is important here, that it selects the largest value of the region to emphasize the strong feature, to find out what is the prominent response. or most prominent response. In this way it is doing. In this position it is 9, so it is 9, and in this position it is 8, so it is 8. Now one thing you have to understand here, now there is a 4 values, now it become 1. So there is a some sort of downsampling kind of thing. Now for these 4 values it is become 1. So this is 4 value, it is become 1. This is 4 value, this is become 1. So from this kind of pooling, this max pooling kind of, for this example, it is in this vertical side and the horizontal side, the row and this row and vertex, it is basically we reduce the dimensionality to this is column by 2 and row by 2. So it was 4 cross 4, this activation maps, now it's become 2 cross 2. So it reduced the dimension also. Okay, so this reduced dimensionality. And what is the effect of reducing dimensionality? The computational cost become less, so accelerate computation. And definitely for this max pooling, it is strengthens the important features over the other responses and provides robustness to translation and noise. That means that if these responses, the other responses, you can see these are the very less response, that may not be a pattern, it may be some sort of noise. So this is actual response, maybe the case. So that is the basic essence of max pooling. Now next thing is called average pooling. Now average pooling is basically this, we can add this number, this is 5 plus 8 and this is also 8, 16 by 4, it is 4. And in this way we can get 4. And it is 12 total, by 4 it is 3. This is become 3 and so on. Now what it is happening? This average pooling computes the mean value of the region. So here the average pooling, it is max pooling is doing the largest value, it taking the mean value. So it preserves overall information. Okay. It in general, if some area is kind of bit homogeneous, then we generally take this kind of overall information or mean information. This is the done with this pooling operation. Okay. Now another important thing that is required to discuss, that is contrast normalization. As you said, that is another important particles of convolutional neural network. So this contrast normalization in CNN is a technique that adjusts the pixel intensities or feature activation to improve feature detection by balancing the local contrast, typically enhancing the important feature while suppressing uniform large intensity regions. Now we have to understand this. What does this mean? So adjust the pixel intensities. What does this mean? So it is, we'll come back in this slide after giving some example. So it aids the handling illumination change. If there is some illumination, I'll give you example to understand properly. Often using methods like local contrast normalization, neighboring pixel subtraction division in such a way. Now I have to take an example to understand. Now consider this image. So there is a face image and you have to do a CNN based face recognition algorithm, that we have to this face. Now if your input a change like this, We can understand that clearly these faces are taken, these images are taken in a different lighting condition, or the illumination are different. This is the case where the light is very less or coming from it from different direction. So where in this local contrast normalization, changes in contrast modify pixel intensity and filter response. Since definitely this, but it is the same image. The challenge of CNN in this situation is that can our model, or can our convolutional neural network model recognize this face in a different lighting situation at the same accuracy of this image where the proper lighting is this. So this kind of situation is handled by this local contrast normalization. So what it is do? Normalization helps the CNN remain robust to contrast variation. So definitely there is a contrast variation, and this kind of contrast normalization is basically robust of this condition. If the contrast of the image change, how the CNN output differ? It adjusts the pixel intensity to balance the local brightness and contrast. So there is a adjustment in the pixel intensity required. Reduce the effect of illumination variation. Definitely there is illumination variation is there, because the illumination is different than this image or that image. And enhance the structural details in the image. Due to the low light situation, some structural differences here, you can say background is very much kind of cluttered with this head, because both are, here it is not that situation, or here this the left ear is not almost visible. So these structural details or kind of details is enhanced by this contrast normalization. Improves feature consistency across the different regions and in regions of the image. That is also by virtue of this. But how we can do this? So here the basic idea is we use this particular formula of this local contrast normalization, reduce the effect of illumination variation and enhance the edge by normalizing the activation left to the local neighborhood. So definitely what we are going to do, this basically the normalization is done by this value, okay, minus m of this mean of this standard deviation. So that is the kind of mathematical formula that this is a kind of normalization formula. By this equation we normalize this, so that even if the response of this, after doing this, response of these two positions are same or very close, so it normalizes the feature values within a local neighborhood. So it's a local neighborhood. And what it essentially do, reduce the sensitivity to this local illumination change, or emphasize the age and texture information, and definitely improve the robustness of the learned feature. Now we understand this, that how by this normalization or kind of contrast normalization we aids the handling of illumination change, okay, or how the pixel intensities are being adjusted for this contrast normalization. This is the basic idea of this. So we summarize this CNN or convolutional neural network by knowing mainly these four important verticals. First of all, convolution. It applies learnable filters to detect features. One important thing is it's learnable. So the filter kernels are being learned when we train our CNN. Then we put nonlinearity. we can use rectilinear unit, linear unit, or sigmoid activation introduce nonlinear transformations, as we have said before. Then come this normalization. This we have given example of contrast normalization. This is an optional step. It may not always be a part of this particular layer thing, but most it is there. And most importantly, pooling this downsample for the spatial reduction invariance. That means that we see how it is for the downsampling the thing, and that is a thing that we can get the prominent response over this, and pooling to some extent produce some sort of invariance, investment scaling kind of invariance there. So these are the major four verticals: convolution, nonlinearity, normalization, and pooling. As we see in this picture, that these four are the main, you can say, submodules in a particular convolution CNN module or convolution neural network module. And if this is an image, now there will be these modules like this. Okay, so it hypothetically said this image, this figure we have discussed before, that this particular layer, it is of this architecture, and it will give the low level feature because it is a very initial layers. Hypothetically, the next layers give the middle level features, the same general structure. Then the third gives the high level features, and so on. And the question is that it is not that, or is that this is a single such layer. It may be there is a multiple layer. There is a 10 such layers for low level features, 15 such layers for mid level features, and again 10 such layers for the high level features, and so on. So by this convolution, nonlinearity, normalization, pooling kind of layers, we get the features, and these features are fed to the fully connected layers. And when we get the values, we get the softmax to get some probabilistic values for the prediction that we have seen our softmax. So this is the basic idea of the CNN as a whole network structures. Okay. So if we say that what is the whole picture, a standard CNN architecture generally includes convolution layers that extract features. So this is convolution layer, activation function, that is kind of ReLU or something that adds nonlinearity, that then the pooling layers that aggregates the over future type and reduces dimensionality, and the local contrast normalization. These all working together to progressively build a hierarchical structure. That is important. This particular structure is a part of this. So this is some sort of hierarchy. Okay, if we recall that in our deep learning definition at the very first state of the deep learning lecture, that we are learning this input in a different layer of abstraction by virtue of a hierarchically defined or in layer wise defined network structure. That exactly we are doing here. And this layer with low level feature, you can say kind of low level, that level of abstraction is less. When you go to the more abstract, the mid level features, more and very complicated features, high level features. Yes, for image example, this is a basically edges kind of thing, this is a shapes kind of thing, that is object kind of, and so on. Okay, so these the different layers learns a different level of abstraction. That is the essence of. Another important thing for CNN, it is that it is a spatial learning. Spatial means image is a spatial structure. There is no temporal aspect. There is no time involved here. So it's a spatial learning. Okay. So that is also very important. In our next course, we will say when we use this RNN, okay, then recurrent neural network, that this temporal thing will come to picture. That we will see next. But here, this is the spatial signal, or the pseudo-stationary signal. That is basically we try to understand what the spatial statistics of this particular signals or image. Okay, so this is the idea of the CNN as a whole for recognizing some image. Okay, now one could see that this ImageNet challenge, this is a very successful in recent times. So ImageNet top 5, this kind of CNN come. Modern Gen Accuracy and Classification Benchmark, 96% CNN is very successful. And this ResNet will come in the next lectures, that this is a very high or very deeper structure. Depth of these breakthrough architectures like ResNet 152. So many layers. And this is the parameters, 60 million parameters. The typical parameters count in the large scale CNNs. So this is the important thing. So where the CNNs are being used for this vision or kind of thing, that object detection, that we'll see. So already we have given some example what do we mean by object detection in our previous lecture. Here we localize and classify multiple objects within image. So multiple object detection using region, proposal and classification heads. This is object. It is CNN is very successful of this. Semantic segmentation, that also we have discussed very briefly. We'll see again these kind of things, that how actual the network is being built to get this kind of done. We already introduced it briefly. So what do we mean by semantic segmentation? Assign class levels to every pixel for dense prediction tasks like scene understanding. This is so why you put it here? For this kind of vision task, CNN is very successful. Image classification, assign single category levels to entire image, the foundational computer vision task. So this is also image. So here you can see that this is some chronological. This is the this ImageNet classification or ImageNet challenge over the year. It is up to 10, and so here there is a GoogleNet. It is 22 layer. Then it is ResNet 152 layers, and you can see the error is very less. Okay, so top 5 error percentage is drastically down. 28 to you can say 3.57 is 2015. So what we can say, the CNN become a very important tool for a deep learning tool for this vision task. So in this lecture, what we have discussed, we introduced convolutional neural network, and then we try to understand what are the basic architecture CNN, that is convolution, what it will be convolution, it will be pooling, and what is contrast local contrast normalization, and then we find what is how CNN used for different image recognition tasks. In the next part, we start the convolution neural network part 2, where different very well-known convolution neural networks such as AlexNet, BridgeNet, etc. we discuss. Thank you.